what would be the product if you do these reactions? Now you see that the organic molecule subject of the reaction is not simple, right? It's not just simple to methane, or it's not simple propane. It actually have a lot of things in there. So you have to start analyzing one by one and see the possibility and then crossing out the impossible one, and then which will get to an answer. It's a bromine with a line. So, I mean, we only have a one reaction to talk about bromination, so it's pretty simple. That's a free radical bromination reactions. So we know that those will make the radical, which will go into the first propagation step, which means it's trying to abstract the hydrogen from the organic molecule. But the question is, which hydrogen, right? There are so many different hydrogen in this molecule. So when you don't know, then you probably have to do all of them, and then trying to cross it out, which doesn't make any sense. And that's going to only leave you probably one choice, or maybe a couple. Then you make the sort out in other ways. So we can see that there are hydrogen on that carbon. I mean, this is not the only hydrogen, but let's start with this one. That hydrogen is very attractive to me because this is a tertiary hydrogen. I mean, tertiary carbon. 1, 2, 3 substituted. So when you take these hydrogens away, you make a tertiary radical. We've been talking about for the radical, the more carbon substitute, the better. Tertiary is actually great. So if you make a tertiary radical and that radical pick up the bromine in the second propagation step, you can make this product. It sounds like a very reasonable answer. So if you put that in the answer for this question, I would say, oh, yeah, at least you deserve some partial credit. That's what I'm saying, but not the correct answer. So what else? Oops. Yeah. This is not. Sometimes the people think that okay, this is a tertiary position, but I like this carbon better because that is a 1, 2, 3, 4 carbon substituted, right? That carbons are more carbon substituted, so more carbons there. Then if you make the radical there, then of course that will be a really nice stable radical, which will be brominated like this. But the thing is, I just made this one out of that thing. You can see that there's 2 methyl groups there. The methyl doesn't go away. First of all, there's no way you can make a radical there because there's no hydrogen. Right? So sometimes the people just thought that the most substituted carbon will go for the answer, and then you just throw this way for no reason, and it is wrong answer. I'm just pointing out that no guess. But first of all, there's no way you can make the radical there because of no hydrogen. And then what this one does, you just take the methyls out and put the bromine there. You didn't substitute the hydrogen with the bromine, you substitute the whole methyl with the bromine. Which is completely wrong. So that is basically, and when I see that, I can guess, okay, this person just guessed. And they just don't know what to do. They just doodle something and then put the things in the most probable positions for no reason. So anyway, so don't do that. That's my message. Then what we need to do, look for the other hydrogen in the molecule. There are hydrogen at that position. This one, yeah, sure, there's a hydrogen there, but this hydrogen is a primary hydrogen, right? This is the one that pick up the bromine, then you're gonna get the bromine at that position, but that's probably not gonna happen because it is a primary radical, no resonance structures, so that is probably the stable one. You got other hydrogen there. This hydrogen is also primary hydrogen. This one, you take it out, you got the radical there, that's also primary. It may produce that, but this will be, we're going to cross it out because there's no reality to that. So I keep saying that primary is bad, tertiary is good, right? So most likely you're going to miss this one. That's another primary carbon. This carbon has just one carbon substituted on it. So that's a primary carbon. So after saying 2 primary, and I've been saying that that's not likely to happen, you're probably going to miss this one too. But the thing is that primary is not the same primary. Because when you take this radical, tightness away, you make the radical. This radical having a benzene next to it. That's the one that makes it different. Allylic position is a carbon next to the other ones. That's allylic. Carbon next to benzene is even more reactive. That's something called the benzylic position. The benzylic position, when you make a radical, this will make a resonance structures. This goes in to here, that goes around the ring by making resonance structures. It makes a total 4 number of the resonance structures. That's the one that makes the benzene very special. It's really stabilizing the radical at the benzylic position. Non-benzene, benzylic position does not mean that any of the rings of benzene. It's actually the carbon connected to the benzene. That's the benzylic position. So let's say you eat food with the benzene on it. Your liver really can make oxidation there by making a radical. It is a primary condition for the metabolisms. It's even more stable than a lyric radical. You can see that how many resonance structures you can draw. So the benzylic position is a really good position to stabilize those radical there. So this is a primary still. So it's a definitely different primary. That no chance of making resonance structures, no chance of making resonance structures. But this one you can. So that will be formed a lot because it's the most stable. This one, take the bromine, and then you get the bromination happen at their positions. And that's a primary bromide, right? So if you don't think about the resonance structures, you most likely guess that may be the major product because that happens with the tertiary positions. But this tertiary radical, that one, we produce that one, that's not the resonance stabilizer. So I would put more weight on this one. So I mean, the tertiary without the resonance structures and primary with the resonance structures, which one is better? It's kind of hard to guess, but I would say that the one with the resonance structures probably better than the just tertiary radical there. It may be competing a little bit, but not a lot. So that's why I say this is probably the most stable radical out of the many that can form. And then when these are formed more, then we will be making these products more. So these two, I crossed it out because those are primary radical with no resonance structures possible. These ones are good contender, I would say that. I'm not saying that that's not happening at all. You may have a little bit of that moving out. So that's why that deserves a partial credit. But I still don't think this is a major problem. My major problem is this. It's all because you're making resonance stabilized benzylic radical. So questions like this for the test. Believe me, it's not simple. You just take the hydrogen away, put the bromine there. Yeah, that's a practice question you see in the book, but not the question you're going to see in your test. You really have to analyze all structures, but the thing for you're going to use the same concept. You just have to follow all the possibilities, and then crossing out which ones are not likely to happen, which ones are more likely to happen, using the principle we talked about, which is stability of the radical and the possibility of the resonance structures, things like that. I normally get a question here. No question? Oh, yes.
So how do we know which resonance structures like the most stable to form?
Exactly. That's the question I was looking for. Great. So if you remember the allylic radical, right? Radical next to local one. Two resonance structures, right? I've been saying that both makes a product. I just show you 4 resonance structures. But why did I use this one for the reaction? That one can make the reaction, this one can make the reaction, and that one can make the reaction. But why did I do that? Why am I missing those things, which I did for the allylic? That's the question, right?
Is it?
No, that's all because of the benzene. Benzene makes a resonance structure by itself. They want to keep the benzene intact. It helps out temporarily, but they don't want to break the benzene structure completely by the reactions, which will be go deep of that concept in OChem 2. So this is a little bit too early to talk about that, but I'm just saying that benzene is a very special because they make the resonance structures, right, which is the circular structures. This double bond will move here, that will move out, that will move over here. So they are really stable by itself. They can temporarily help it out by carrying some charges inside the ring, but they don't want to break the structure of benzene in the end. So they were kind of I would say, they're not really, they can be a good pool of the resources. When somebody needs some money, they can lend it out, but they don't want to run the business by themselves. They want to just help them. So that's the reason these resonance structures are stabilizing this radical there, but these are not participating in the reactions. You only see this one going for the product. Yeah. If there's a no benzene in there, there's no resonance structures possible, the only thing that can be used for the figuring of which is the most stable one is a degree of substitutions. So if there's a low benzene ring, I would say this one would be the major product without the benzene there. But the thing is, if this is not benzene, it also produces other position. That's also tertiary position too. That can be also participated. So that will be totally different question. We have to solve it out that one separately.
Sorry to go back, but I remember with bromination, we actually sort of assume that it's 100% to the one product because it's just so much different compared to bromination. But when we're looking at the allele or the fluid group, why do we say that there's two products? Because I know there are two resonance groups, but one of them is it's the third degree, but one of them is the first group. Why don't we focus on the third degree?
So you talk about the previous one, right?
Yeah.
Because they are resonance structure, they both exist. One's the radicals are, they're not two structure going back and forth. That's what we're mentioning, they're in equilibrium. The two structure has to be exist basically to make an equilibrium. The resonance structure, the 9%, they don't exist. It's a kind of a two structures are shown to show that what would be the actual structure may look like. So one structures having radical the torsion position A is so you should have radical 70% there and 30% there. We can split up there. So that's why resonance structure is difficult to be valid because we give separate structures, but you have to bear in mind that neither are true. There's a one true image is there that's carrying all the things combined together, but then something that are really equal. Those cases, the tertiary radicals are more contributing. So I would say maybe 60% radicals of tertiary condition, 40% of the other conditions. So that's why both will go for the separate radicals. Yeah, just one structure. So that's the things that you got to differentiate actual structure in equilibrium and the resonance structures. All right, so anyway, this is a kind of a thing that I know is difficult, but you see the reasoning that I give you to figuring out what is going to happen. So after teaching this, I'll probably, before I do that, I just want to say the same thing. There is a hydrogen on the benzene too, but these hydrogens, not the subject of the halogen reactions. So that's what we're talking about. Yeah, that takes out, you make the radical on the benzene, that make the bromine, you get the bromination there. But this is not happening because of these hydrogen carbon bonds on the benzene, sp2 hydrogen carbon is a way more stronger than that. So it doesn't come up. So do not try to use a hydrogen on double bonds or benzene. That's what I keep talking about. sp3 carbons, not sp2 carbons, right? Hydrogens on sp2 carbons are not subject to the halogenation reactions. And then for the same reason, all the reaction in these chapters, substitution reaction, not going to happen to sp2 carbons either. We primarily focus on just sp3 carbons. Anyway, so that's that. So this is something that I want to tell you before I move on. So now you see this question. I guess you've got the good image of this what we did. Okay. Then what I'm going to probably ask in the test is this. It looks pretty similar, right? Almost same to you, probably. If you don't pay attention, or you saw pages maybe an hour ago, now you can look at that and you think that, oh, that looks pretty similar. So what you probably like to do, follow the same process. Yeah, I'll be talking about benzylic position. These ones are very good. So this bromination there, that will be the answer. Because I'll be talking about that makes a very stable benzylic radical. That was answered in the previous slide. Let me remind you, right? This one. This is a makes a benzylic radical. That's the one that makes a reaction with the bromine. You get the bromination there. That was an answer, right? So after seeing that, you see this, and you see the same thing. So most likely, you're gonna pick this one as a major product. Because it looks so similar. I mean, you already solved the other one. And then I'm saying that is wrong. There are other hydrogen there too. I mean, obviously, these ones are saying they're two, but we talked about that makes a tertiary radical without the resonance structure, so probably not a good one either. But there's a possibility to that. I kind of crossed that one in the previous example because there's no hydrogen before. But what I did do this question, I put the hydrogen there. I take the methyl groups out, the hydrogen there. Now, we can make a radical. So first of all, the same thing can appear. This radical can pick up the hydrogen from this position. That makes a very stable benzylic radical. I'm not denying that. That is a good one to make. And then but there's a tertiary radical can be also formed too. But we already talked about that is probably not a good one because these are resonance stabilized. That's not a resonance stabilized. So not a good one. But this one, that one wasn't there before. That's the change I made. It's only one changes. I just take the method away from the previous example, and it just showed a new possibility, which means that hydrogen, if you take it out, that's a radical next to benzene. There's another benzylic radical. It can make a resonance structures. So that's a benzylic, but the this thing that benzylic with just one carbon mounted, benzylic and primary. We get that one. That's 1, 2, 3 tertiary carbon benzylic. So benzylic and tertiary. So if you're going to compare stability of the two benzylic radical, then this one is probably bring to the top. Benzylic and tertiary will be more stable than benzylic and primary. Then which is the most stable? That is not the most stable radical. This is the most stable radical. And that's what they pick up the bromine, then makes this as a major product. So this is how question will be confusing to you. It looks similar, so you are going to be lured to the answer that you've been giving, but that one difference is change the thing. So that's what you really have to sort it out.